Welcome back to another lesson related to trigonometry. Today we will be discussing Ptolemy's theorem. Now, Ptolemy's theorem basically states that any quadrilateral, that is any four-sided figure that can be inscribed in a circle, has this neat property. The product of the diagonals is equal to the sum of the product of opposite sides. I've color-coded this to help you visualize. AC times BD is equal to AB times CD plus AD times BC. That's the general form. Unfortunately, my chalkboard is not large enough to complete the derivation in one view, so I'll have to go over that separately. Stick around if you're curious for the details. But now I want to look at a particular example, revisiting our friend the pentagon. Because the pentagon is a regular polygon, it can be inscribed within a circle. Of course, the pentagon has 5 sides, as seen here. But what if I chop off this triangle and I simply deal with the remaining trapezoid? Then I have a 4-sided quadrilateral, and I can apply Ptolemy's theorem. If the side length of the pentagon is 1, 1, 1, 1, leaving the unknown side length of x. Now, back to our previous video on similar triangles, we know this is isosceles, so the diagonal is also x. So, plugging it into Ptolemy's theorem, x times x equals x times 1 plus 1 times 1. Simplifying brings me to x squared minus x minus 1 is equal to 0. Solving that with the quadratic formula, I come up with x is equal to phi. Feel free to revisit that video and brush up on the connection to this special number and the unique properties it has. I have transcribed our diagram from the chalkboard to this sheet of paper. Instead of diagonals, I have now split the circle into 4 arcs, AD, DC, CB, and BA, and 4 central angles corresponding to those arcs. I define these to be 2 alpha, 2 beta, and 2 gamma. On the right, I have drawn central angle 2 alpha separately. Notice this is an isosceles triangle with side lengths R, R, and AD. By cutting it in half, there are now 2 similar right triangles that are symmetric to each other. Being a right triangle with angle alpha, I can use trig ratios. Sine is opposite over hypotenuse, so sine alpha is equal to AD over 2 over R. By rearranging, I get AD is equal to 2R sine alpha. A similar argument can be made for CD and BC, as shown below. Because a complete circle has 360 degrees, or 2 pi radians, the central angle corresponding to arc AB is equal to 2 pi minus 2 alpha minus 2 beta minus 2 gamma. Half that angle is equal to pi minus alpha minus beta minus gamma. Then I plug this into my angle sum identity to find that side AB is equal to 2 times r sine alpha plus beta plus gamma. Lastly, AC is equal to 2r sine alpha plus beta, and BD is equal to 2r sine beta plus gamma. Take a look at the diagram to convince yourself. Here I have stated Ptolemy's theorem for your reference. We substitute side AC for 2r sine alpha plus beta, and so on for the other side lengths. Next, I divide each term by 2r to cancel that out. In the second to last line, I've expanded each term on the left-hand side using the angle sum identity for sine. Finally, I FOILed everything out and summarized my result. In a similar fashion, I've expanded the terms on the right-hand side. Sine of alpha plus beta plus gamma requires me to apply the angle sum identity twice. Then it's simply a matter of distributing all my terms correctly. The main purpose of splitting this into the left-hand side and right-hand side was to conserve space and make it easier to digest smaller chunks at a time. In order to prove Ptolemy's theorem, which we started with, I simply need to demonstrate that the left-hand side is equal to the right-hand side. This is done below. In case you are wondering, I color-coordinated terms to show which ones cancel out and which ones factor. That leaves the following. Notice the Pythagorean identity. Cosine squared of beta plus sine squared of beta is equal to 1. Algebra shows me that indeed the left-hand side is equal to the right-hand side, and Ptolemy's theorem is valid. Here's a snapshot of the grand scheme. Earlier in the video we showed how Ptolemy's theorem can be applied to the lower trapezoid of a pentagon to find phi. Ptolemy's theorem can be useful for many other things. For example, if we inscribe a rectangle in a circle, Ptolemy's theorem spits out a neat connection to the Pythagorean theorem. Are there any other applications you can think of for Ptolemy's theorem? Let me know down below in the comment section. Don't forget to like and subscribe if you want to get updates on more videos like this. I really appreciate your support, and look forward to seeing you next time.